proving this beautiful formula using Fourier transform. So there is this beautiful result from vector calculus, right? Which is also like applied in electromagnetism and other fields. And over here, the formula states that that's nabla cross f is equals to nabla of nabla dot f minus nabla square f, right? So here, f is actually a vector over here, right? A vector function. And the nabla is also a vector, but this is a vector of partial x, these operators, partial y, partial z, right? And these things over here. So this is basically the curl of f. I guess you know it from the vector calculus, right? And this is the, what do you call it? Divergence of f, right? And then similarly, nabla of f, this is just gradient of f, right? So now for this one, to find the gradient, it should actually be a scalar function, right? Because yeah, you actually take a scalar function, and if you find its gradient, you get a vector, right? So this is gradient of f. And also for this Laplacian operator, I guess you guys know the Laplacian operator for scalar function, right? So this is just the divergence of the gradient of f, right? So that's how it's defined. But there's also a version where you can find Laplacian of like the vector function, and that's defined as if you want to find Laplacian of this vector function, right? So let's say the vector over here is, let's say, fx, fy, fz, right? Then its Laplacian is defined as just the Laplacian of fx, Laplacian of fy, Laplacian of fz. So that's how it's defined. Okay, so now that you know all these terms, like what do they mean, I think we can proceed ahead, right? And also let's before going ahead, let's do a little sanity check if this operators make sense. So over here, so first of all, okay, this is a vector and this is also a vector. If you do cross product, you're gonna get a vector over here, right? Then you can also do cross product of two vectors that allowed. And again, so this is a vector, so cross product is allowed, and again you're gonna get a vector. So you will get a 3D vector here, right? So over here, so both of them are vectors, so you can actually take dot product, which is like divergence of f. So this is gonna be a scalar, right? After it's a scalar, you can actually take its gradient and you will get a vector over here. So yeah, makes sense. You are getting a vector over here. And similarly, because this f is a vector and you are taking this Laplacian vector, you will get a vector over here, right? So just like over here, Laplacian of f gave you a vector over here, right? So yeah, it does make sense. Now the only thing is we need to prove it. And we will prove it using Fourier transform. And before I go into proof, I need to share a few things about Fourier transform for vectors, right? So I will just write a definition and then I will write some results and then you will use those results to prove it. So, okay, for a vector function, right? F of x. So define the Fourier transform in this way. Okay, the Fourier transform, which will then be like function of the k. Also, this k is also a vector, right? So in like from Fourier in k space, in Fourier space. So basically, this the Fourier transform of f whose input is like this k vector. So like this k vector, each of them correspond to its variables, right? And in r cube e to the power minus I k x. Here when I write it like this, please know that that's a vector. Or I can also actually do it this way, is to make it easy, to make things easy to understand. And then f of x vector dx vector. So yeah, so using this definition, we can actually define Fourier transform also for vectors, right? And now if we use this, then the following formulas are valid. So now if we have a gradient of a scalar, right? Uh, then let's say we have gradient of some function f. Its Fourier transform will just be I times k vector multiplied by the Fourier of this f function, scalar function. So this will just be a vector scalar multiplication, right? Similarly, the divergence of a vector will just be, so divergence of there's this vector function, right? And if I take the whole Fourier transform of this whole thing, let me manage a little space over here because it seems congested. Its Fourier transform will just be I times k vector dot f vector, right? And its Fourier transform. So basically, using this definition, like for a vector function, we can just take Fourier transform of each component, right? You can see that because you can just write it as in the component form, and you see that it's essentially same as taking Fourier transform of each component. So that's how you can do this whole thing. Okay, now similarly, another formula for curl of a vector. So the nabla with f, its Fourier transform will just be I times k vector cross f vector, right? Okay, and then after that, for Laplacian, so Laplacian of a vector, right? So basically, this k vector is consists of all the variables in the Fourier space. So there's this a Laplacian operator of f and its Fourier. So this one will just be negative of the magnitude of k square times f vector, right? So we are gonna use these things and prove it. So now over here, so we want to prove that this nabla cross f is equals to nabla of nabla dot f vector minus Laplacian square of the f vector, right? Okay, we start with LHS, right? So if we take, so what we're gonna do is we're gonna first of all take Fourier transform of the LHS, and at last take the inverse Fourier transform, and we'll get the results. Essentially, what we can also do is we can also just take like the Fourier transform of both sides and so that they are same. So for now, what I'm gonna do is I will just take the Fourier transform of the LHS, and at last I will take the Fourier inverse transform. Okay. So if I take its Fourier transform, so from the formulas here, we know that this is just gonna be I k vector cross I k vector cross and then f vector Fourier transform, right? So now I can just take these constants out. So this is minus k vector cross f vector, right? So I times I is -1. So now this is just the a vector cross b vector cross c vector, right? This is like the vector triple product, right? And from vector calculus we have a formula for this, right? So we cannot use that we cannot use that formula directly here because these are just operators, but now these are actually terms. So these are actually things, not just operators. So the formula from vector calculus is that, so b vector a vector dot c vector minus c vector a vector dot b vector. Now the reason it makes sense is that the final result should be perpendicular to a, right? So that means it will be like spanned by b and c, and it cannot be done by a, right? So it will be spanned by b and c. So now you can actually prove this using that idea, because you can actually from the fact that this whole thing will be perpendicular to a, you can write this as like some x times b vector plus some y times c vector, and try to solve for x and y. That's how you can derive this formula. Okay, so if we are going to use that formula now from vector calculus over here in our scenario, so if we use this formula, we will have minus of the, okay, so first of all b vector is just k vector, right? And then yeah, and also note that these are just some scalars. These are just some scalars for B vector and C vector. B vector and C vector are actually the vectors, and these are just numbers that will be in front of them. So yeah. Yeah. So okay. So B is K vector in this case, and then K vector dot F vector minus C is F vector in this case, and then K vector dot, I can write K vector as like this instead of hat. The hat makes it unit, that isn't necessarily unit, right? Okay, K vector dot K vector, right? Okay, so now this becomes minus, I can actually write this as ik vector, there's a reason for that, times ik vector dot F vector, right? And plus this is now this magnitude of k whole square with F vector, right? Okay, now notice that like this thing is actually just the Fourier transform of the divergence of F, right? Yeah. And now like if I say that this whole thing, let's say if this whole thing is just some function, let's say g, then ik vector with some, okay, now this is a scalar, right, with some scalar z function, then this is just the what do we call this, what was the word again, gradient, just gradient of z, right? So this whole thing is essentially just the gradient of the divergence of F vector, right? So yeah, so I think you see that from here. So first of all, if we just take, okay, so now from here you can see that this whole thing, first of all, the inside part is just the Fourier transform of the divergence of F, right? And over here I can write this as minus with minus magnitude of k square F vector. And now again, this can again be written as, now this is just a scalar function, right? So scalar function with ik vector, that's just the, what was the word again? Gradient. The gradient of the divergence of F vector, right? So its whole transform. Okay, minus, and now we know that this is just the Laplacian, right? So this is just Laplacian. Yeah, Laplacian operator and the Fourier transform. So we now see that this nabla cross F, the Fourier transform is that, right? And now since Fourier transform is linear, I can actually get this Fourier transform to the whole thing and then take Fourier inverse in both sides. Yeah, this is one side. And then, so if we do that, we get nabla cross F vector is equals to the thing that we wanted. So that's it. We have proved the statement. Thanks for watching. Yeah, so we just proved the statement that we wanted, right? So we already proved this, but I also thought that I wanted to give an example, right? So that it's more clear. So let's just do an example of this formula holding true, and we'll conclude the video. So let's say if I take F vector as e to the power x, y square, xz, right? So let's first find left hand side. Nabla cross F vector, okay? To find this, first of all, we should just find nabla cross F, which is just I, j, k, partial x, partial y, partial g, e to the power x, y square, xz, right? So this becomes I, that's just 0 minus j, and that's, okay, so that's z, right? And then, okay, is that z? Yeah, that's z. G minus 0 plus k with 0 minus 0, right? Okay, so that says minus a j of z vector. Yeah. Okay, so now that we know that, let's again find this nabla cross of F vector. So we already know the inside thing, nabla cross F. So let's use that again. I, j, k, partial x, partial y, partial g, right? And then we have this 0, because here in this nabla cross f we essentially have 0i plus 0g, right? 0k, right? Okay, so if you use that, 0 minus z and 0, so this turns out to be I 0 minus minus 1, right? Plus j, and then 0 minus 0 plus k. Okay, so there should be a negative sign over here, I'm sorry. So minus j, 0 minus 0 plus k, 0 minus 0. So that's essentially just 1 comma 0 comma 0, right? Okay, so that is our this thing. Now let's try to find this nabla of nabla dot f minus nabla square f, okay? Okay, first of all, just nabla dot f. So this is just partial x of e to the power x plus partial y of y square plus partial z of xz. So that's e to the power x plus 2y plus x, right? Okay. So now again, if we try to find the gradient of this scalar thing, we will get, so first of all, there's a vector. So first one is just x derivative, right? The second one is just y derivative, right? And third one is just z derivative, right? Okay, so now if we use that, so this is gonna be e to the power x plus 1, and then just 2, and then just 0, right? Okay, so this is our gradient of the divergence of f vector. Now, if you want to find the Laplacian of f vector, so this will just be Laplacian of the first component e to the power x, Laplacian of second component, which is y square, and Laplacian of third component, which is xz, right? And now again, to find Laplacian of e to the power x, we need partial square x by partial x square of e to the power x plus partial y square of e to the power x. This is a lot of thing to do actually. But this, in our case, it will be simpler. Let's just write the results directly. So in our case, if we do partial, no, let's do it. There's no reason to skip things, right? Okay, and then partial square by partial x square of y square plus partial square of partial y square of y square plus partial square of partial g square of y square, and then partial square of partial x square of xz, partial square of partial y square, there should be plus here, of xz plus partial square by partial g square of xz. So that was a lot of thing to do, but I did it. Okay, now this becomes this becomes e to the power x itself, because these two terms are just 0, and from first term it's e to the power x again. And okay, here these two terms are just 0, and from second term we get 2y and then 2, right? And here this term is clearly 0, and even these two terms are 0, because if you differentiate twice with respect to x, first of all it's z and then it's 0, and here again same, first of all it's x and then 0, so last term is also 0, right? Now if you take this difference, or this partial of partial dot f, this is nabla minus nabla square f vector, this is just e to the power x plus 1 to 0 minus e to the power x to 0. So that's just 1 to 0. So you see, it actually matches, no? This both the things over here, this one as well as this thing over here. Oh wait. Okay, I did the wrong difference. It should have been 0. I'm sorry. This is 0, 0. Okay, and over here on the left hand side, this is nabla of nabla dot f minus nabla square of f vector. Okay, yeah. So then it becomes this thing and this thing. Yeah. Okay, yeah. So you see that those things are actually equal. So yeah, that also verifies our result. And yeah, so that means we have definitely proved it and also gave an example. So I hope you enjoyed. Actually, like for me, these results are really fascinating that how nicely they work even with this vector derivatives things, like this vector derivatives like divergence, gradient, call, even with these things, it works pretty nicely. Yeah. And like you might also want to check on things like firms. Like these are also pretty awesome tools which also generalize these things like this gradient divergence call as derivative. So which definitely look like derivative over here as well, right? This was pretty cool, guys. I hope you enjoyed the video. The proof was also interesting. Thanks for watching, and I look forward to seeing you in the upcoming videos too.